Hello everyone. In this video, I am going to discuss the work presented in a very landmark paper in plasma physics, popularly known as BGK paper, named on the basis of authors Bernstein, Green, and Kruskal. The work done in this paper is remarkable as for the first time they were able to obtain exact non-linear solution of plasma oscillations. In general, whenever we come across a nonlinear solution, we try to linearize it by approximations and then we obtain certain solution. But in this paper, they have obtained exact nonlinear solution without involving any kind of approximation, starting from the Vlasov equation, and that is quite remarkable. So, in a plasma, we can have electrostatic waves. What do I mean by electrostatic waves? Usually when we have a time-varying electric field, then that leads to generation of a magnetic field component. But in plasma we can have time-varying electric field without having any component of magnetic field. If we look at Maxwell's equations in plasma, it is possible to make del cross E go to 0 and we can balance the physical current with the displacement current, hence making the magnetic field 0. So these are electrostatic waves, that is waves without magnetic counterpart. We can obtain linear solution for plasma waves by gathering linear terms as we have solved in our class. But the linear solutions obtained were not quite satisfactory. It presented some difficulties associated with particles trapped in the potential energy troughs. So the aim is to solve coupled Boltzmann and Poisson equations and obtain exact nonlinear electrostatic wave solutions. Now let's study the system and corresponding assumptions to be considered. We are dealing with collisionless plasma in this problem, that is, as plasma particles evolve in time, then total volume of phase space remains constant. We are also dealing with quasi-neutral plasma, that is, plasma is composed of equal number of ions and electrons. The plasma is completely ionized, that is, no neutral particle is left in the plasma. In solving the equation, we assume that we have not applied any external electric field. And so, the potential phi that is present purely comes from plasma. It is developed due to plasma ions and electrons. And we are working in frame of Vlasov equation. That is, we start our work of solving nonlinear equation starting from the Vlasov equation. Now let's look at the formulation of the nonlinear problem. We will be working in the wave frame so that all quantities are time independent. These are the two equations that we need to solve. First one is the Boltzmann equation and second one is the Poisson equation. In the first equation, F plus is the ion distribution and F minus is the electron distribution. M plus is the ion mass and M minus is the mass of electron. Here there should be a dou F by dou T, but that is equal to 0 as we are in the wave frame. Also, dF by dt is 0 as we are working with collisionless plasma. We can always shift from wave frame to lab frame by Galilean transformation as we are in the Newtonian regime. Here in this equation, phi is the electrostatic potential, v is the velocity, dou phi by dou x represents electric field due to potential phi, and so minus E by m dou phi by dou x represents the force term. So we started with Vlasov equation and we have obtained equation 1. Now let's discuss this equation 2. So in this Poisson equation, we have F minus, which is the density of electrons in phase space, and when this term is integrated over dV, then we obtain density of electrons in configuration space, and multiplying this term with E gives the charge density of electrons. So here there should be a negative charge, a negative sign. So a negative sign is taken from this side to this side and that's why we have positive here. So now our aim is to solve equation 1 and 2 exactly without any approximation, and get we need to solve these two equations and get consistent solution for phi. So one can write energy for the particles as E plus is equal to half m plus v square plus E phi for ions, and E minus is equal to half m minus v square minus E phi for electrons, where this part is the kinetic energy part and this is the potential energy part. Also, we have solved for Vlasov equation, and we know that the general solution of equation 1 is that our distribution function should be a function of Hamiltonian. Here, Hamiltonian is energy itself, and that's why we have distribution function as a function of energy here. Now, if we replace V with E everywhere in equation 2 and dV with dE using this equation everywhere in this equation, then we obtain equation 5, which is essentially the same Poisson equation. So if we substitute E, which is a function of phi, we have here phi on both sides of the equation and the equation becomes nonlinear. But we will be solving this nonlinear equation. Let's go ahead and study some additional constraints. So apart from equation 1 and 2, there are some other constraints as well. So if we consider a potential of this form, then for such a potential we have this as our phi max and this is our phi min. And if there are ions with energy E phi, and if we choose phi such that phi is greater than phi max, then our ions are in this region and they are freely moving in region A. But if phi for ions is less than phi max, then they are either in region C or in region F. Once in this region, the ions are trapped in this region and they bounce back and forth here. This is because once the ion reach here, then its kinetic energy becomes 0 and so it can't cross the barrier. If it tries to cross this barrier, then its kinetic energy becomes negative and velocity becomes imaginary, which is physically not possible. Hence, it is trapped inside. Ions in different regions are disconnected. Ions trapped in region C and that in region F are independent of each other, and these are further independent of that in region A. They don't talk to each other. F is not same for all ions. Similar is the case for electrons. For electrons having energy minus E phi, if the energy is less than minus E phi min, then electrons are trapped in the region B or D, and if the energy is greater than minus E phi min, then electrons can move freely. The trapped electrons or ions need to be equally distributed between the two directions of velocity, and so F minus and F plus for trapped particles need to be symmetric, while for untrapped particles there is no such restriction. So let's look at the first approach of solving the nonlinear problem. The first approach we have is the differential approach, in which we fix distribution functions and solve for potential. Differential approach is many to one approach. So if one prescribes F minus and F plus, that is our distribution functions, then equation 5, this equation, can be represented in this new form, which can be easily solved numerically. We can solve equation 7 by quadrature and we can obtain solution like this. It is many to one approach because for different choices of distribution function, we can obtain the same potential phi. The next approach is the integral approach, in which we fix phi and try to find distribution functions. So if we consider this equation, d square phi by dx square is equal to minus ne phi, where n is the net charge density, then we can obtain equation 10 from equation 5. It involves some mathematical steps. Equation 11 is the density of trapped electrons. So if we are given phi, then we can find d square phi by dx square, and hence we can find ne phi. Further, if the entire ion distribution is known to us and the distribution of untrapped electrons is also known, actually we can assume the ion distribution and distribution of untrapped electrons. Then we can use this equation, equation 11, to get GE phi, and we can then find trapped electron distribution easily by using equation 12. The idea is that we can obtain various portions of our phi bit by bit using this approach and stitch it together to get entire phi, which further obeys rules like d phi by dx is equal to 0 and d square phi by dx square is continuous at the extremum, guaranteeing continuous charge density. This approach is one-to-many approach. As for a particular potential, we can obtain various distribution functions. So there are some important points to note. So both approaches are fine and give satisfactory results, but the differential approach is many-to-one system and integral approach is one-to-many systems. But this is actually not a problem. Ultimately, both approaches need to be consistent with each other, which they are. If we have fixed phi potential and we obtain distribution from integral approach, then if we use this distribution in differential approach, we should get the same exact potential phi. Another thing to notice is that we obtain no dispersion relation for non-linear waves. We can have arbitrary wavelength. Omega by k is also arbitrary. Wave velocity is arbitrary. So arbitrary Galilean transformation can take us from wave frame to lab frame. So no one-to-one correspondence between wavelength and wave velocity exists, or one-to-one correspondence between frequency and wave number also does not exist. So in linear waves, we had this dispersion relation being followed, this one, and to satisfy this, to make integral not blow up for any value of v, we need to make omega imaginary, and if we do so, we find that linear plasma waves decay and loses energy. There is some dissipation. While the exact nonlinear solution of the same class of Poisson equation tells that plasma waves without any decay do exist. So they don't follow any such dispersion relation, and so their omega need not be imaginary. Omega is arbitrary, and so plasma waves without decay exist. And this is a very remarkable finding. So we conclude that in this paper they have solved the nonlinear plasma oscillations and have obtained some remarkable results. So that's all for this video. Thank you so much.